So we do a lot of y of t as well. So a lot of the motion we do right now is in two dimensions. So x of t typically indicates we're going left or right along an x-axis. Y of t typically is indicating we're going vertically up and down along a y-axis, what our most common general problems are. And if it's not specifically stating left, right, or up and down, you'll see an s of t. It really doesn't matter how it's named, but those are the three most common that we're going to deal with. We know then that the derivative of position is our velocity. That's a single tick. We know the derivative of velocity is acceleration, or the second derivative of position. All that we know. The thing we want to visit now that we haven't talked about before is this kind of new idea for us anyway, the idea of speed. Velocity we have talked about before. Speed is similar to velocity. Speed is the absolute value of velocity. So the difference with this now, if you remember, velocity tells us our direction. If we had a velocity that was positive, we were going to go right or up, or basically our position increases. If our velocity was negative, our position decreases. So that typically meant left or down, with the context of our problems that we've been doing. When I ask you for the speed, we don't care about our direction. Speed is strictly how fast we are moving, regardless of if we're increasing our position or decreasing our position. So while they're very, very similar, and this is sometimes hard for people to kind of wrap their head around, they are not the same thing. Okay, velocity is a little bit more descriptive than what our speed is. So that idea is somewhat new. And then these ideas. So where you see these two different things, we see the idea of distance versus displacement. Both of them, you're going to see how understanding these are both a type of position. They're different ways of measuring a position. So both of them are going to have us integrating our velocity. But if you notice, if I want the distance, we're not just integrating the velocity, we're integrating the absolute value of the velocity. And we just define the absolute value of our velocity as the speed. So in order to figure out our total distance traveled, we want to integrate our speed, which is really the absolute value of our velocity function. If I simply want displacement, we're just integrating our velocity. All this is, we're using fancier words right now, but all this really is the same thing we would have talked about before. Like if this is my function and I'm going to integrate that function, let's say this is 4, from 0 to 4, and let's say this has an area of 2, this has an area of 3, and then we assign a negative to it because it's below. It's the same thing we've been dealing with. If I wanted the distance, then I want the absolute value of these, so the distance would be 5. And if I want the displacement, it's a -1. It's the whole idea of area versus our net change. But we're just going to use some fancier words, and it's now exclusively to our velocity function. Okay? So these three ideas here, somewhat new in terms of how we're defining them and how we're going to be using them. And then that's kind of what we dive into here these next few days. So for number 1, where we're going to kind of introduce this, I give you a velocity. So I tell you the velocity of something moving along a line over the interval of 0 to 3 pi over 2 was given by this function. So the first thing I want us to do is just graph this. We'll do this on the paper. You don't necessarily have to pull out your calculator for this. And we're going to make our x intervals 90 degrees. So just make this pi over 2, pi, and then 3 pi over 2. Cosine values, we know over here at 1, the cosine of 0 is a 1. Since we have a 5 in front of it, we know we're going to jump up to 5. The cosine of pi over 2, we know is 0. The cosine of pi is a -1, but since we have a coefficient of 5, we're down at a -5. And then the cosine of 3 pi over 2 we know is a 0. Now, we kind of skip some steps. So when we connect these, don't draw these as if it's a line. We all know what the cosine curve looks like. So just kind of sketch it in like so. And then we're going to label this so that we know this is our velocity function. So recall some old ideas that we want to revisit now. I mentioned it up here a little bit. When I start taking off at the time of 0, notice how my velocity is above the x-axis. So this entire time, I am moving to the right. Remember, when our velocity touches the x-axis, that's when our velocity equaled 0. And then not only does it just equal 0, it's changing from a positive value to a negative value. So if you recall a really old idea, that means we're changing directions at this time. And then once we swing underneath the x-axis, so now this entire interval, our velocity has negative values. So this entire time, we are moving to the left. So off to the side, let's draw this kind of in 2 dimensions. So let's say this is Nick going for a run after he proves that 0 is equal to 1. We say that Nick is going to head off to the right. So initially, he's going to go to the right. It's increasing his position. At the time of pi over 2, he has this momentary stop. So this is going to be pi over 2. And then we know he moves left to the rest of the way. So here he comes to the left. All right, so that's what it looks like if we actually look at our position. We go right, come back left. We would have changed at pi over 2. And then we stopped at 3 pi over 2. All right, so now letter B. If I ask you to find the total distance, and then letter B, total displacement, hopefully we kind of understand the idea of distance versus displacement. Let me not assume that. If we go out to the track right now, and I run around the track 4 times, my distance is 1 mile. Right, we all agree with that. My displacement would be 0 miles. We haven't changed our position at all. So keep that straight. If we look at what Nick's position looks like, there's no way our distance and our displacement should be the same. It's possible, the way I drew it in anyway, that he finished right where he started from. Okay, now we're going to show kind of what he did, how much he traveled in each direction, but we should definitely get different answers for this. So when I go to find my total distance, using our little definition from above, so this guy right here, in order to find the total distance traveled, here's what we would currently need to do before we talk or use the formula from above. Notice how we change directions at pi over 2. So I'm going to set up one integral from 0 to pi over 2. And I'm going to integrate my velocity multiplied by my change in time. So again, velocity times time. So like meters per second times second is going to give us our meters. This would tell us how far Nick moved to the right. Then I want to figure out, well, how far did Nick come back to the left? So that would be the integral from pi over 2 to 3 pi over 2. Once again, integrating that velocity times our change in time. Now, in this case, we can definitely use our calculators. Again, I'm going to kind of just give these to you as a way to save a little bit of time. But just do a Math 9 on this, or if you would have graphed this on your calculator, you can use the cool shading option. What we would find when we do this on our calculator is that this has a value of 5. So what that means is he traveled 5. What unit did I give you here? Meters. So he went 5 meters to the right. So if I come back up here to my beautiful graph, we're going to show Nick went 5 meters to the right. If I then integrate pi over 2 to 3 pi over 2, that same velocity function, when I do that, that's going to give me a negative 10. And understand why that is a negative 10, right? Because that's the area that's underneath the x-axis. That also tells us, when we go ahead and assign this to Nick's little path up here, that if I give this a negative 10, so again, a little review here, displacement with a negative value means our position decreased by 10 meters. So if I were to ask you this question right now, before we use any absolute values or anything, we talk about that, right now what you think his total distance traveled would have been in our little model here. All right, and Nick, since you're here, how far did you travel, Nick? Good. So Nick put down 15 meters. So there's now 2 different ways that we can kind of approach this. One is what I have up here. We don't just want to integrate the velocity. We want to integrate the absolute values of these. So we could have taken the 5 meters to the right, 10 meters to the left, and we just add these using the absolute values. That would give us our 15 meters. If we just use our diagram here, we know we went 5 to the right, 10 to the left. It's a total of 15. Okay? This is kind of our old way of doing it. It's a little bit longer, setting up multiple integrals. What we're now going to do, so we'll do this over here, is our new way. And the new way is, instead of having to split these up, set up multiple integrals, do some absolute values, we're going to basically just set up what I am telling you to set up when we talk about distance up here. So go ahead in that integral, set that up. We're going to integrate the absolute value of our velocity. So that's our velocity function. We're not going to worry about the change in directions because the absolute value bars are going to take care of that for us. So we're just going to do the entire interval of 3 pi over 2. When we throw this into our calculator, it better spit out the same value that we just got here. So you have probably done this maybe at some point in your life. It's probably been a while, but the absolute value bars. So when we go to plug this into your calculator, clear this out. You're still going to do your math 9. We're going 0 to 3 pi over 2. So all that we know. So get to this step here. And then we now need the absolute value bars. And then within the absolute value bars, we're going to put that 5 cosine of t. So you're going to find that underneath, find your math key right here. You'll click on that guy. And then if you move over, I think it's numbers. I hope it is. If I remember, yeah. See the ABS? That's clever. Stands for absolute value. So click on that. And then you're going to see your absolute value bars. From there, it's pretty self-explanatory. Go ahead and plug in your 5 cosine of x. Put your dx here. Hit enter, and then you're going to notice most of you, I haven't put this in yet today, so we're going to find out how smart my calculator is. But some of you are going to notice a little bit of an error here. Let's see. Okay, do a lot of you get this here, this little extra at the end? So the calculator has issues with 2 things. One of them is irrational numbers, so that's why sometimes an irrational number gets off a little bit at the end. It also has a little bit of an issue with this absolute value. What the calculator is doing, it's actually doing the absolute value of this curve. So it's actually taking this segment here, or that part of the graph, and it's then flipping it upwards and accumulating the change within that area. When it does that, it creates kind of this little sharp corner here. And it just has a hard time in terms of integrating when we are dealing with that idea of a sharp corner. All right. So don't put the 15.00000 and then whatever those were, 459. Our answer is 15. We know that because we just did that, split it up, and we got exactly 5 and exactly 10. That then right away gives us our 15 meters, and we no longer really have to worry about splitting up our integral if that's the case. Okay. Now, letter C. Find the displacement. So just right away, tell me that answer. We've already kind of done the work. You're going to be able to say that answer right away. All right, Arushi, what was our displacement there? You're not sure.
Would it be subtract 2 this time?
Yeah, sort of. You did.
Yeah,
good. So it's going to end up being a negative 5. All right. So we went 5 units to the right. Then we came back 10 meters to the left. So when we get our displacement, us just adding these guys up. So what we would do in this case is when we add them, we just don't worry about the absolute values. And that's going to give us our overall displacement. This tells us that we end up 5 units to the left of where we started from, or that our position decreased by 5 meters. However, the model is setting this up, but we definitely decrease our position by 5 meters. If we don't want to split it up, all we now need to do is just go 0 to 3 pi over 2. And I'm just getting this from up here. This is what we've been doing now for a while. This gives you the net change. When we just integrate our function without absolute values, that's going to give us our net change. Wait, it's cosine, right? So if I now do this without absolute value bars, so if I do the same exact thing, I'm not sure if I can delete absolute value bars or not. Let's see. Yep. Hit enter, and then that's going to tell us that our displacement's a negative 5. All right. All right, so that's basically kind of the new stuff a little bit. Distance, you're going to integrate the speed. That's the absolute value of our velocity. Displacement, we're just integrating our velocity. Now, there's a lot of little tweaks to this, and we're going to do a graph here in a moment. But that's the basis of everything that we're doing here today. So go to number 2. on the next page. And again, some old stuff here that we want to bring back, at least A, B, and C. Because all this is going to come back to us. So in letter A, what you're told is this is now a position function. All right, so just know that. Moving along the x-axis, so that means our motion, we would talk in terms of left and right. And then our time is just greater than 0. Our x is measured in meters, time is going to be in seconds. So in letter A, all I want you to do is show that we are moving to the right at the time of 0. So old ideas, we just talked about it up here with our graph. I know I'm moving to the right when my velocity is positive. So it's a velocity question. So for letter A, if we're moving to the right, we are thinking, when is my velocity greater than 0? Right? Is my velocity greater than 0? So to find our velocity, we know that's our derivative. So go through that. So we're just taking the derivative of our position up here. And then I'm asking specifically about the time of 0. So really all we're looking for is, what is my velocity at 0? So this is our velocity. So if you want to put v of t instead, you could. At the time of 0, my velocity is 8, and then we'd have units of meters per second. That's largely the answer. That is us showing that since my velocity is positive at that time, we are going to be moving to the right. If I ask you to justify these, which I've done, that's what you would basically say, is the velocity is positive at that time. Okay. Now B, I don't ask you to evaluate it at a particular time. Now I want to find any time when we are moving to the left. So if the velocity being positive moves us to the right, then we recall we're going to go left when our velocity is negative. We already have the velocity equation. This t squared minus 6t plus 8. We're trying to figure out, when does this equation here have values that are less than 0? So this goes way back to all of these where we would set it equal to 0. Quick little factoring, and then remember all the sign charts that we did endlessly in chapter 4. Those are back. We really don't want an arrow on this end. We do have this endpoint. Since we can't have a negative time, I'm also telling you that up here, that our time has to be greater than or equal to 0. Do your sign chart real quick. Break up the cobwebs in your head from those from a while ago. So figure out what are our signs in that interval, in those intervals. Once we have that, we're just looking to see what intervals do we have negative values. And then we can go ahead and now write that as when we are moving to the left. All right. Hopefully, wrong thing. All right, hopefully when we do our signs, what do we get? All right, we all get positive at the beginning there. Yeah, and then no tricks with this one. These should alternate nicely. So positive, negative, positive. So here is where we're moving to the left. So we are moving to the left, starting at 2 and concluding at the time of 4. All right. All right, letter C. I want to know what's the position at that time. So this is super easy. I want to show us something on the calculator we kind of already have done, but it's going to become pretty important in this one. So this is your position function. So all we're really looking for is, if I took a 3, plug it in right here, what's that going to evaluate to be? But here's how we're going to do this. This is ultra easy. You're going to see on our third day of this, there are going to be times when this is an irrational number, or a decimal that extends well beyond 3 decimals, and we don't ever again want to round and use that rounded answer in our calculation. So I want you to we did this the other day, and you had to do this on the quiz yesterday, hopefully. Store your x value as 8. So take your 8. Was it 8? Is that what I gave you? What time am I looking for? 3? Okay. I don't know where I got 8 from. So let's go back. So store 3 as your x. Oh, I know why I got 8. And the thing that you're going to want to use, especially when this is an ugly, ugly number, we wouldn't want to take an ugly, ugly number and plug that in and put a parentheses and cube it, and then put it in for this t and square it, and then enter it again. We would just like to have it stored. So now that it's stored, we can just enter this expression directly into our calculator, and it'll do all the work for us. We don't have to worry about order of operations. We don't have to do all that work. So you're going to do 1/3. Let me see if I remember this. 1/3 t cubed minus 3t squared. So now if I just make this look like our function, so 1/3. And then now that I know the x is stored as a 3, so I just do 1/3 x cubed. I already forgot it. What is it, Rishi? What's the rest of that equation? All right, minus 3x squared plus 8x. So again, if this is an ugly decimal, this is a pretty efficient way to do this pretty quickly. Store it one time, throw this in, calculator does the order of operations, and that answer is 6. So we find at that time, our position would be 6 meters. So storing this isn't a big deal, but as we prep for in a couple of days when it gets ugly, you're going to want to make sure that we know how to store that. And then letter D, answer letter D. I'll give you a minute. This was the only real new thing today that we talked about. See what you think for letter D. Okay, let's see what we got here. So all I want to know, what was the total distance we had traveled after 3 seconds? So our old way of having to do this, we would have had to have seen over here, we changed directions at 2, and we would have had to have gone from 0 to 2, 2 to 3, set up multiple integrals, do their absolute values. Now that we can just do one integral, we can just now go from 0 to 3 right away. Just make sure we don't forget the absolute values for distance. Make sure you're doing it with your velocity. This was our velocity right here, so that's the function that we're plugging in. Whatever that gives us should be our answer. All right, and again, it might be just a little bit off. In fact, it is a little bit off, so you won't be able to do the little convert into a fraction. But that answer is, does it come off a little bit on your calculators? Yeah, because it should be, what is it, 7 1/3? Yeah. So it's probably on your calculator 7.33333, and then these last couple of decimals are probably going to get off a little bit. If you're integrating an absolute value or a radical, it is a reasonable conclusion to make that this is 7 1/3. That's just a little bit of an error created by the absolute value. So our total distance we would have traveled would be 22/3 meters. All right. All right, last one before we get to this AP question on the next page here. So the function v of t is the velocity, so it's a velocity function. I'm going to have you do 3 different things. While I don't label it A, B, and C, let's label them that. So letter A, what I want you to do first is to graph this function to see where our velocity is positive and negative. All right, so again, probably normally have you graph this on the calculator and all that, but we know this is a line. We can do this pretty quickly. Our y-intercept is 8. We have a slope of a negative 1.6, and then we're going to go to 10. All right. If we figured out where does this equal 0, just to see where we're going to cross that x-axis at, what you're going to see is that's at 5. So at the time of 5, we cross our x-axis, and we look like this. And then keep in mind, we are looking at a velocity equation. That's all I want you to do for part A. Recall what this all now means. We're moving to the right. We change directions right here, and then we begin to move to the left. Letter B, second thing I want you to do, find the distance. So set that guy up real quick. Make sure we got a handle on that. And once you've got that, because that should be pretty quick, you can go ahead and do letter C. The third thing I'm asking you to find is the displacements. All right, so B, total distance. We're going to be integrating our velocity from 0 to 10, but for distance, we want the absolute value. And then displacement, you're going to set up something very, very similar, minus the absolute values. Okay. All right, Andrew, what did you have for the distance here? Was it? Good. Should get 40. And then what's our displacement? Good. And our displacement would be 0. Now, don't flip the page, because here, this problem is what I kind of use to transition to what we're going to be doing in this next page. If you have your function, then we can use these formulas here. We can integrate the absolute value of our velocity, or we can integrate the regular velocity. We can answer these questions. Well, let's say none of this was here. Okay. I can never do this normally, but let's say that wasn't there. And we couldn't then set this up because we don't know what that equation is. And that's sort of what the next question is, right? We just have this graph. We're not necessarily given the equations, while we might be able to figure them out. But if we have this graph, we should be able to answer these questions the exact same way. Because if I now want you to answer the distance, if I integrate velocity, so this is what we've been spending the last 2.5 weeks on, when we integrate a curve, what are we finding for that curve? When we integrate a curve, it is the what of that curve? Carter? It's the area. Okay, so when we integrate a curve, it is the area. So if I find this area right here, isn't this really just a triangle with 1/2, and then the base is 5 and the height is 8? So that's of what, 20? So that would have told us we went 20 meters to the right if we just found the area underneath there. If we do the same exact thing down here, we'll get the same exact numerical value of 20, but it's going to be negative. So by using the idea of area, and the area as an accumulation of change, as the integration of a function, or in this case, a graph, couldn't we get the exact same answers that we would have gotten without having to know what our function is? So if I did the absolute values of both of these and added them, we get the 40. If we just added those up as a net change idea, we're going to get our displacement of 0. Okay? That's, most of you are in physics now, have already had physics. You would have done this plenty of times when you were doing that stuff. Okay? All right, now, let's go to the next page. We'll get started on this. We'll see where we finish. This is one of my favorite questions because it now makes you know how to do these things with both models. So what this is telling us, get rid of that, is you've got two runners. So you have runner A, you have runner B. They're going to race on track for 10 seconds. The graph above, which is 2 line segments, shows the velocity. So that's something we want to be aware of. This is a velocity graph of runner A. So runner A is the graph, and it's a velocity graph. So we'll label that as runner A. And then the next question is, the velocity in meters per second of runner B is this guy. So we have a graph to work with, but we also have an equation to work with. And then if we understand all 3 of these ideas, position, velocity, acceleration, A is asking us for our velocity, B is the acceleration, C is our total distance. So we've got to be able to maneuver back and forth from our velocity using either a graph or an equation, either model, an algebraic model or a graph model. So letter A, find the velocity of runner A and the velocity of runner B at the time of 2 seconds. All right, so let me try to do this because we're not going to be able to see it all. So A, we'll do runner A, runner B. I think in this case, runner B is the easiest one, so I'm going to do that first. Runner B is the equation. So if we know runner B's velocity is defined as 24t over 2t plus 3, we just plug in 2, and we would get 48 over 7. Notice how this now asks for units of measure. So what you want to be careful of, all of them ask for units of measure. You don't get 3 distinct points for units of measure. If you mess up one of those 3 units, you don't get the unit points. You have to get all 3 A, B, and C's correct of the units, or you wouldn't get the 1 unit point that they've assigned. So that's something you want to make a note of and make sure we don't screw something like that up. That should be free points. So our velocity, in this case, they're telling you is in meters per second, that function. So we know that functional value is meters per second. Then we need runner A. So if we look at our graph, we've got to use the graph for runner A. We want runner A's velocity at 2 seconds. So velocity graph, here's the time of 2 seconds. Tell me what you think. Write down what you think that is, or at least have a strategy, or what do you think the answer is? Okay. And hopefully, as you're contemplating or doing this or whatever, hopefully you're not the kid. So please don't be this kid that comes over here to 2 seconds and says, I'm just going to mosey on up to my graph right about here. And maybe it's 7, maybe it's like 6.5, maybe it's 6 2/3. Unless it's 5, like I can go up from 5 and know that I'm at 10. But at 2 seconds, do we really know by this graph what the value is? It's somewhere in here, but my guess, if we had to guess, we'd all come up with something a little bit different. So don't just do that. All right, don't just kind of figure what that is. There's a couple of different routes. Anybody think they got it? Because there's really 2 different things we could do to figure this thing out. Yeah, Steve, what do you got, Steve? It is 20 over 3, so that's good. So let's go to runner A down here. And his velocity after 2 seconds is 20 over 3, and then that would again be meters per second. And what was your thought process, Steve? How did you do it? Good. He basically calculated the slope, right? We go up 10/3 of a unit for every 1 second. So after 1 second, he would have been at 10/3. After 2 seconds, he would have been at 20/3. All right. Good. Anybody else do it a little bit differently? It's kind of the same. The other route you could take then, if nobody did this, the reason this one's easy, I think, is because you have the equation. Don't we know how to write the equation of a line very quickly? Like if we were to go ahead and put this into a point slope form, we have everything we need. Steve just gave us our slope to be a 10/3. We know you could pick 310 or 0, 0. You're being silly if you don't use 0, 0. Well, isn't that our equation now? And now can I just plug in 2 and it's going to spit out a 20/3 very quickly? Okay. All right. So either route, that should be 20/3. All right, let's try to get B done. Because runner A should be really, 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 really easy. Write down what you think the acceleration of runner A is at 2 seconds. Not 1/3. Where'd you get 1/3, Emma? Okay. If I'm at velocity and I want to go to acceleration, isn't that our derivative of this? And what have we said since the first couple of days of school? Doesn't the derivative mean the slope? Didn't we already figure out the slope of this line? Didn't Steve give us the slope of that line as 10/3? That then is your acceleration. So runner A's acceleration is 10/3, and then that's meters per second squared. Okay. Then runner B, what time do we got? Think about how you would answer this question. If we want the acceleration of runner B after 2 seconds, we would now need to take the derivative of this equation. Remember the good old-fashioned quotient rule? Yep. We don't have to use a quotient rule here. Okay, this is something I'm going to show you on your calculator that I don't want you to use before today. So on your calculator, go to your math button and look at number 8. See where it says n deriv? So instead of math 9, which you just took a whole quiz on yesterday, go to number 8 where it says n deriv. We want to take the derivative with respect to x. And then now the equation we want to take the derivative of is this equation here at the time of 2. So just make this look like the problem on the paper. So on the top, so you're going to create your fraction, do 24x over 2x plus a 3. Then we have our little evaluation bar here. The calculator wants to know at what x value do we want to calculate this at. We want to calculate it at 2 seconds. Hit enter, and voila, that's our answer without having to go through the quotient rule. There's 2 parts to the AP test. One's with the calculator, one is without. This is one of the 4 things you need to be able to do with your calculator. All right, and now you know how to do it, so now we can use this moving forward. So this is your answer, 1.469. All right, with that, we're going to probably have to call that a day and wrap up letter C tomorrow. Because we got like 15 seconds left. But if there's any questions, you can stick around a minute, let me know, and then we'll finish this off tomorrow. Okay, and then we'll probably go over the quiz tomorrow too, hopefully, if we can get everybody made up. All right? Okay, we'll see you guys. Have a good day.